Hey class, this is Gigi from Kauai Community College. In this video, I am going to try to summarize to you the whole entire idea of what you're supposed to be learning in this class. And then at the end, I want to be able to find the number E, okay? So here is what we started out with. We started out with saying that the polynomial approximation of a function f of x is going to be approximated by the polynomial f of a plus the derivative evaluated at a times x minus a plus the second derivative evaluated at a over 2 factorial. And here really is 1 factorial, and this is 0 factorial. And as we know, 0 factorial is going to be 1, and then 1 factorial is still going to be 1. So, but I didn't need to write the 1 on the denominator. So that is why we usually don't see that there. Okay, now so this is going to be x minus a to the second plus the third derivative evaluated at a, x minus a to the third, and then we have to divide out 3 factorial and so on, right? So that is what we would do in a polynomial approximation. So here we're trying to get to the number e. So I want to know what the polynomial approximation is for e to the x. And here I want to be doing that near or center at a equal to 0. Okay, so we would say then we would go ahead and use this table here to guide us and to figure this out. So first, initially we'll start with the function f of x is equal to e to the x. Evaluating that at 0, we will have an a right here is being 0, right? So e to the 0 power is 1. So the coefficient is f of a, which is 1. And then the first derivative is, lucky for us, still e to the x evaluated at 0 is still 1. So then we will have the derivative divided by k factorial. That would be 1 divided by 1 factorial, and that is still 1. Okay, so these are your coefficients right here. And then the second derivative is going to be still e to the x. Evaluating that at 0, you will have 1. So the coefficient is going to be 1 over 2 factorial, and that would be 1 over 2. Okay, next, the third derivative is going to be still e to the x. Evaluating that at 0, you will have 1. And then so the coefficient is going to be 1 over 3 factorial, and that would be 1 over 6. And then if you go further and keep taking the derivative, it's going to stay e to the x. So then evaluating that at 0, it's going to be 1. So your coefficient is still going to be 1 over k factorial, which is, in this case, 1 over 24. So these are your coefficients. So you would say the polynomial approximation, and really I went up to 4, so that will be the fourth polynomial approximation to this function is going to be 1 plus 1 times x plus 1/2 times x squared plus, and a, remember, is center at 0, so we don't have to write x minus 0, right? And it's going to be 1 over 6 x to the third plus 1 over 24 x to the fourth. And this is what we call P4 of x, which is the fourth degree polynomial approximation for e to the x near 0. Now, if we let this to go further and go infinitely, we will have a Taylor series. And in this case, well, is it a Taylor series? Is it a Maclaurin series? What is it? Well, a Taylor series is centered at any value a, and here is center at 0. Okay, so Maclaurin series is just a special case of the Taylor series. In this case, I really want to find the Maclaurin series for e to the x. And if we observe the pattern, we will see that e to the x is going to equal to 1 plus 1 over 1 factorial times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x to the third plus 1 over 4 factorial times x to the fourth, and so on. So we would then say e to the x is equal to the series x to the k power on the numerator, and then on the denominator you will have k factorial. Now, where are we going to start for our index? We want to start with 1, so we must have k equal to 0 as our starting point, and that will go all the way to infinity. This is what we call the Maclaurin series for e to the x, and that is being centered at 0, right? So when we call that something a Maclaurin series, we know that it's centered at 0. Okay, now that we have a series for e to the x, what we want to know is for what x value will that work? Okay, now that means what is the radius of convergence, or what is the interval of convergence for this series? Because we want it to converge to that function, right? So for what x value will this work? So if we really think about what we are doing here, here is the center. Center is at 0. And we want to know how far out can we go? Meaning, what is the radius of convergence? And then what is the interval of convergence? So, and in order to do that, we have two choices, either the ratio test or the root test. Well, I am going to take the ratio test for this one. Okay, so applying the ratio test, I need to go and find what is the limit as k goes to infinity of absolute value of a sub k plus 1 divided by a sub k. Now, we are going to find the limit, and then we're going to say in order for this series to converge, the limit is going to have to be less than 1. So let's first calculate the limit. This is a fraction, so division means multiply by the reciprocal. So I'm going to plan ahead there. Okay, so what I have is x to the k plus 1 over k plus 1 factorial divided by k factorial over x to the k power. Now, if I was to go and simplify this, I would have limit as k goes to infinity. And let's just look at the k first. K factorial divided by k plus 1 factorial. Well, the k factorial won't going to be divided out. The only thing left is going to be 1 over k plus 1. And I don't need to write that in the absolute value form because remember what k is. K is from 0 to infinity. So it's a positive number, and so I don't need the absolute value there, right? However, the x here, I need the absolute value on that x. There are k plus 1 copies on the numerator, and there is k copy on the denominator. So k copies will cancel. That leaves us with 1 left on the numerator. Okay, so to think about this here, we would say when k is going to infinity, we are only looking, when taking the limit with k going to infinity, we're only looking at this part right here, right? Because the absolute value of x is not being affected when k goes to infinity. So when this happens, we will have 0 multiplied by the absolute value of x, and 0 multiplied by the absolute value of x is always 0, right? No matter what x is. So, and that is always 0 no matter what x is, and 0 is less than 1. Okay, so what we are saying is this series that we're looking at always converges no matter what x is. Okay, so we would say converges no matter what x is. So what that means is that our interval of conversion is going to be all the way to the left and all the way to the right. And I'm not sure why that erases what I was writing. But you will have, here you go, interval of conversion is going to be everywhere on the number line because the limit is 0 no matter what x is. So we would say this series hold for e to the x. We would say e to the x is going to equal to the series going from 0 to infinity of x to the k power over k factorial everywhere. Okay, so everywhere, no matter with x is from negative infinity to positive infinity. It's everywhere. It really doesn't matter. Okay, so what are we looking at? I said in the end, I want to use the series here to estimate what e is, right? So we would say then, since e to the x is equal to 1 plus x over 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and so on. And that is equal to the series going from 0 to infinity of x to the k over k factorial. Now, that is when that is true for any value x, right? If it's true for any value x, it must be true for x equal to 1. So e is e to the first power, right? So e is going to equal to, so wherever I see x, I will put in 1. So that would be 1 plus 1 over 1, which would be 1, plus 1 over 2, plus 1 over 3 factorial is going to be 6, plus 1 over 24, and so on. And really, that is the series going from 0 to infinity of 1 over k factorial. Okay. Now, even if we were only going out to, let's say that many, it depends on how far you want to go, right? So what I want you to be able to do now at this point is to go ahead and get over to decimal and see that calculation. I mean, already you see that E is going to be, right here, is going to be 2 plus some, right? Okay, the question is, what is that if you were to keep going? And so it's like 2 point something. You know E is 2 point something, right? So let's go and since we have this wonderful decimal calculator, we don't need to go and use do this by hand, right? I mean, in the golden days where there's no calculators or software that will do this, then people would have to sit there and do the calculations. And like you would kind of have to appreciate where all of this math come from, right? But anyhow, since we do have a calculator, let's go take a look and see what E is. So, okay, I'm in decimal. I'm gonna type in, the the series here and do let decimal do the calculations for me. Now you already know if I go out to 1, that means 1 plus 1, right? That's the 2 that you have seen. And then if we go out to 2, then it will be 1 plus 1 plus 1/2, which is 2.5. So far so good. And then if n is going up to 3, then that would be 2 plus 1/2 plus 1/6, right? So which is giving you that right there. Now let's go very far out. How far do you want to go? Well, let's go to 10 and see what E is. If you go up to 10, that right there is what the approximation is for E. Now let's go out to 100. Wow, look at that. Didn't change that much, right? Let's go out to 1,000. You don't even see any changes. Let's go out to 10,000. You don't even see any changes. So this really is a really, really, really good approximation for what the number E is. So there you go. That's a really good beginning to end of the story of what it means to for this unit, right? So we started out with polynomial approximation. That's our first lesson of this unit, right? So first we say we started out with polynomial approximation. And then we say, well, here is this approximation right here, okay? And then we say, hey, what if we let it go infinitely? Well, when it go infinitely, then we will have what we call a Taylor series. And in this case, since it's center at 0, then we have what we call a Maclaurin series. So the second part of our lesson is to be able to observe a pattern and be able to write the series like that in the yellow box. And then the third lesson that we are looking at is power series. This right here is a power series. And given a power series, we are to be able to find the radius of convergence and interval of convergence. And to do that, we use what we call the ratio test. And when we use the ratio test, we need that limit to be less than 1. So in this case, the limit is 0, which is always less than 1. So our radius of convergence is infinity, and our interval of convergence is negative infinity to positive infinity. So this series here is true for all x values, okay? Is true for all x values. So if it is true for all x value, then it must be true for when x is equal to 1. So that means e to the x can be approximated with this series right here. Plug in x equals 1 for wherever x is, right? So wherever x is, you plug in x equal to 1. And we went and used our decimal calculator, or if you have a scientific calculator, you can also punch that in. And we can see that the value that come out to be is approximately 2.71828 for when k is up to 10. If we have gone out all the way to 10, that's the value. And if we change it to like 100 or 1,000, it doesn't change that much. So this right here is a really good approximation for the number e, right? Now, what if I ask you, what is e squared? Well, what are you going to do? Well, you are going to put 2 in for x, right? So that would be that plus 2 squared over 2 factorial plus 2 to the third over 3 factorial, and so on. And then that would be the sum from k equal to 0 to infinity of 2 to the k power over k factorial. And what you could do is go to decimal and use the summation function to do the approximation, and you would be able to get e squared. Okay, so that's one application of the Taylor-Maclaurin series. And the other type of application is we could use the polynomial to maybe replace what e to the x is when we're looking at the limit. We could actually use the integral, we could do the derivatives, and so on. And that's what's going on in the fourth lesson of, this is the fourth lesson of the chapter, which is to go ahead and apply these series to different applications.